That way you always have a backup.
All right. Good afternoon, everyone. My name is Pravi. I'm a research scientist at ORNL, and I'm the chair for this year's data challenge. And this is the kickoff webinar for the SMC Data Challenge. So welcome, everyone. Okay, I cannot see the number of people here. Okay, no, I can't. So how many people do we have on? Oh, fantastic. We are getting more participation. So in this data challenge, I will talk more about what the data challenge is about, where it will be held, when it will be held, how the registration happens, what are the different data challenges, and the sponsors themselves, the data sponsors themselves will talk about what their challenge is about and what is the scientific importance of that one, what the tasks are and what is expected, and give the participants some tips to get started on the challenge. And we'll also talk about registration and also submission, and your like if for all the winning participants, you'll be invited to present at the conference, as well as invited to publish as part of the Springer CCIS journal, which is the book that is published for the Smoky Mountain Challenge. So so let's start with the website of just so we can get started on that one. Let me start with the website so I can explain what this is about. Can you see which screen can you see? Okay, so this is the website for the Smoky Mountain Challenge. So the Smoky Mountain Data Challenge is a small part of the conference of the bigger conference that is ORNL's annual conference, and this is the 5th year of the data challenge. So what happens is there are data sponsors. So it happens every year in August, and this year it is from 25th to 27th of August. And where it is going to be held, whether it'll be virtual or in person, or it'll be a hybrid conference, is still under presentation and still under discussion. So you'll always have a chance to know, you'll always have an option to present virtually if you cannot come in person or not allowed to. So that's a very open question at this point yet. So the registration for there are 8 data challenges this year, as you can see, like 8, and there are 2 categories of data challenges. And the first category is the data analytics challenge, and the second category is the data edge computing challenge. So the first 6 of the challenges belong to the data analytics category, and the next 2 belong to the edge computing category. So all the and then here is the call for papers. The challenge is open from May 10th until June 25th or 2021, which is everyone who wants to register and participate in the challenge should register by June 25th. So the paper and your solution papers are due by July 27th. And then the program committee of the data challenge will send you notifications by August 13th, whether you're a finalist, whether the solution was acceptable. And also you'll be judged based on whether you're a novice or an advanced scientist in the field. And so so for all the selected posters, last year it was in the form of a lightning talk instead of a poster. Because it was virtual, everyone was given a chance to give a 3-minute lightning talk based on what their solution was for each challenge. And so this year, the lightning talk or poster presentation will be on August 25th, the second day of the conference. And the final paper notification, and then once all of these people all of the presenters will be invited to submit their papers for a Springer conference. So one of the things is because of that is a peer-reviewed journal. You'll be given a chance to, and then all of the final paper notifications of your submitted paper will be sent out by September 3rd, and the camera-ready paper is expected to come back by September 14th. So that's that. And so the paper submission needs to be done we'll go through the registration first. For all the participants will either register as a team or an individual. I think we have about 15 registrations right now for different challenges. And if you're an individual, you'll have to select which challenge that you're going to solve. And then we'll also, if one of the things I'm trying to do this year is try to identify people who need a mentorship and then connect with the sponsors if they're willing to give that kind of support. And so this is where you'll do the registration. And then once that registration is done, you should be able to submit the paper, and once you have a paper ready via Easy Chair. And this is where the easy chair is. Like, so if you want to make a new submission, you'll go to make a new, you'll log in, make a new submission, and select this particular track, SMC call for papers, and then do your submission. Register all your all the members who are part of that challenge, and submit and upload your PDF, which should give us access to your solution. So that is about the website. And also one of the things I wanted to show is, okay, and also for going through the challenges, this is how the challenges are done. So you go to the challenge webpage, and then you have a drop-down list of all the different challenges. So here the title and all the sponsors and what the challenge is about, the introduction, as well as the importance of that particular challenge. And there are also questions, the data sets itself. There are data sets that are explained about what the data sets are about, or how many, or basically the nature of the data set. And then there are questions, the challenge questions that are pertaining to the data set. And these challenge questions go from easy to hard. So even if you're a novice person with not really much experience, you'll have the chance to go through them and then only solve the basic challenges based on what your ability is. And again, we'll try to give you as much support as possible. And for that, you could join the Slack channel and ask sponsors directly the questions that you have, and also try to connect with other participants. And I think that would be a great way to be a little bit more collaborative than doing it on your own. So you can refer to these challenge web pages, and each web page will have a data set. And this year, the data sets, you're able to download them through a DOI, which is a digital object identifier. And to download that, you need the setup, and all of the instructions for downloading are in the form of video, which is on the website, on the challenge web page itself. And then once you click on this download button, you'll have a PDF copy of the challenge web page, which is exactly what I think is in here. And so you can also challenge you can also join the challenge Slack channel. For each challenge, there is a separate public Slack channel that you can join. And the main contact person for the sponsor, the main contact sponsor is here. Or if you have also any questions, you can ask either via this email, or you can also ask the person, or also join the Slack and ask the sponsor directly via that channel. So that's about the challenge. And right now, I think we are ready to get our sponsor started on what the challenges are about. Let me do a new share of the presentation, just so. All right. Let me share the main. All right, let's go through that. We did navigate the web page. So our first sponsor is from CNMS, and Ganesh, you can take over and explain your challenge.
Yes, Pravi. So hello, everyone. My name is Ganesh, and I'm here to talk about my data challenge. The title of my challenge is Unraveling Hidden Order and Dynamics in a Heterogeneous Ferroelectric System using Machine Learning. So ferroelectrics are materials that have spontaneous electric polarization. And this polarization, it can be reversed when you apply an electric field. So I don't know if you are seeing the slides, but if you are, then you will see that on the top right, there is a loop. And this loop is formed between the polarization of a macroscopic ferroelectric material when you apply an electric field, where the electric field goes from 0 electric field to something positive, and then goes back to something negative, and you sweep back and forth. But you find that the polarization does not trace back the same path.
I'm sorry, I'm sorry for interrupting, but I think no one is able to see the slides.
Okay, that would help. Thanks, Maxim.
Slides now.
There it is. I see the loop now. So this feature that the path that the polarization takes when you sweep this electric field is not the same path up and down, and forms a loop. It's called a hysteresis loop. So it's related to a lossy mechanism in the material and many properties of the material related to this loop. Now, even though the material that I'm interested in is a classic material called barium titanate, whose schematic is shown in here. Even though the global polarization of the material follows this loop, if you look at the small repetitive unit, which is what I show here, each one has a polarization as well. And that polarization could be very different spatially. And that's what I call the local polarization. And this variation of the local polarization is what I call it's like the hidden order in the system that we really don't know a lot about. So if you look at the schematic on the left-hand side with the orange and the blue figure, so what I plot here is the local polarization. I think the slides have moved. Can we go back to slide 2, Ravi?
Okay. Yeah. Please let me know when I should move the slides. Just so.
Yeah, perfect. So here, if you sum up the polarization, it's 0, but locally you see a lot of variation, and you see regions with between up and down polarization, which is called a domain wall. And this feature, this local polarization and its variation is very different if you have heterogeneity in the system. So heterogeneity such as missing atoms, missing oxygens, or missing bariums. And in the bottom right, you see another snapshot where you find that this local polarization shows a different variation compared to the case where there was no defect. And in the inset, you see this hysteresis loop, and you again find that the hysteresis loop, which is related to the global switching of the system, it's also very different. Not only is the static snapshots different, but also the dynamics, that is over time, how things change, are very different when you have heterogeneities. And what we are really trying to understand is how to represent the local variation in the polarization as you change the either the system size or heterogeneities in the material. And how do you capture the dynamics of the material, particularly the local polarization in the material when you change these heterogeneities? And hopefully by understanding and capturing those, we can understand what really affects the change in the hysteresis loop. If you go forward, Ravi. So we have provided 2 types of data sets. The first is the local dipole, which is basically the polarization of every unit cell, the 5 atom that I showed, in my big box of simulation as a function of time. So you have the time step, you have the box dimensions here, and then you have the coordinates of the unit cell and the polarization, which is a vector. If you go to the next slide. We also provide for some of the cases a VTK file for the same data set, which you can view in the ParaView software program. It's a visualization program which I used to create that orange-blue image that I showed in slide 2. Next slide. Yeah, so the first data set that I have is for the equilibrium dynamics, so 0 electric field, but I just run a very long simulation for these 4 data sets, set 1 with no defects, and 2, 3, and 4 with different kinds of defects. Next slide, please. And the second data set, which is a little bit larger, is it's a data point for, again, these 4 sets of data. So that is no defect and 3 different types of heterogeneities. But now the simulation data is there for every point in that hysteresis loop. Next slide. So the main challenge question is how do I extract and represent the states with different dynamics? So the local polarization states with different dynamics from an MD simulation, such as the one that I shared with you. possibly using graph neural network methods. How do these states evolve when I apply an electric field? And how can I understand the change in the hysteretic response or the hysteresis loop based on the representation of these states and their evolution under the field? That's my challenge question. And thank you for helping me with this.
Thank you very much. And next challenge, we'll have Dasha talk about the knowledge graph link prediction.
Hi, Pravi. Hi, everyone. Thanks for having me. So my name is Dasha. I'm a research scientist at the Learning Systems group in the Data and AI section at ORNL. And so I'm here to present on behalf of the team about the challenge, finding novel links in COVID-19 knowledge graph. So if you can go to the next slide. So the goal of this challenge really is to develop methods for discovering novel, previously undiscovered relations between biomedical concepts that were extracted from a concept graph built from scientific literature, and specifically literature about COVID-19 and other coronaviruses. So as you all know, the speed with which we generate new data is increasing at incredible rates. And this is also true for research literature. We're at a point where the volume of scientific literature or scientific publication is well beyond the capacities of anyone. And so really the goal of this challenge is to assist the discovery of potentially novel relations between existing concepts. So this whole challenge is motivated by what's called Swanson linking. So the scientist Don Swanson in 1986 proposed that dietary fish oil could potentially be a treatment for Raynaud's disease. And what's interesting about this discovery is that he read a lot of biomedical literature and he noticed a connection. He noticed that Raynaud's disease has high blood viscosity as a symptom. And he also noticed that fish oil reduces blood viscosity. This was in two sets of publications that were completely disconnected. And so he proposed, based on this connection, that this could be a treatment, and it was indeed verified in a clinical trial years later. And so based on this discovery, he suggested that perhaps a way to discover these novel links is to look at these transitive relations between concepts. So if you have concepts A and C that have no known relation between them so far, but there is a third concept, B, that is connected to both A as well as to C, this may actually indicate a plausible novel relation between A and C. And so the goal of this challenge is really to try and see if this discovery can be automated in some way. So if you can go to the next slide, Ravi. Thanks. So what you see on the right is a small snapshot of the data that we're providing to you. So in the graph, the yellow nodes that have a number above them, those are research publications. And the other colors, the other nodes, all represent different concepts that were extracted from these publications. And the links between them always represent relations. And the thickness of the edges also represents how frequently they are connected to each other. So the main file that we're providing to you that I would encourage you to look at first is the CSV file called edges.cc, which essentially contains a list of edges between concepts. And the concept IDs in the files are actually IDs that refer to this UMLS ontology that stands for Unified Medical Language System. And so you can actually use the IDs to collect additional information about the concepts, like what relations they have to other concepts that might not be included in this particular snapshot of the graph and so on. And so there are two links on the slides. I will also add them to the GitHub repository that I'll show on the next slide, as well as to the Slack, so that you can look at these. Yeah, and so there are also other files that provide information about how the concepts are related to publications, or to be more specific, which publications were they extracted from, as well as file that indicates how publications cite each other. And so there's also a link to a publication that describes the data in more detail that I will also post on the Slack, as well as on the GitHub page. And if you can go to the next slide, Ravi. So as for the challenge questions, as a first step, I think it would be interesting if you could analyze and visualize the provided graph. So really just take the edge list, construct a graph from it, and see if you can look at statistics like between a centrality, or what's the average shortest path length between concepts in the graph. As a second step, I think it would be interesting to look at novel links. So when I say novel links, those are links between concepts, between nodes that previously did not have a connection between them and have just been connected for the first time. And so how many of these are formed per year, for example? And it would also be interesting to look at things like any of these statistics above, do these actually correlate in some way with occurrence of these novel links? And so as the next two steps, and those are the main questions for the challenge, it's to see if you can develop a classification model that essentially takes the available data or anything else you can collect from external sites as input and predict which concepts will form next, or which concepts will form a connection next. And the same for the ranking step, which is the fourth question. Instead of classifying, can you develop a model that actually ranks these predicted links? For example, according to the time they will form, or how many publications will link them in the next year. And so here's the data page. I'll also put that on Slack, and that's everything I had for the challenge. Let me know if you have any questions. Thanks, everyone. Thanks, Ravi.
All right, so it's essentially a link prediction challenge and identifying the importance of the links. So could this be done with graph algorithms? So, okay. We'll move on to the next one. And also next speakers, can you just try to keep it under 5 minutes just so we have like equal space for a lot of other people. And the next we have Jordan and Pri. I think Jordan is presenting and they are from General Motors, okay?
Okay. All right. Good afternoon, everyone. It's Jordan. I'm a researcher from GM, and I'll be speaking about Challenge 3. So Challenge 3 is about domain adaptation, and so what this refers to is a model's ability to transfer well across different domains. So it can be different weather or you know, changes in hardware, changes in lighting, all these things. So we'll be looking specifically at going from real world images to virtual world images. And so the task is to develop a network that's able to do this very well, to generalize across these different domains very well. So why are we interested in this? Well, we're interested obviously because we want reliable, robust networks that are able to, you know, generalize well to new domains, new weather or new lighting, all these things that could maybe, you know, not be in the training data. And more than that, this would also help to reduce the overall time that we need to, you know, develop and validate and all these things. So this will, you know, permit us to hit the market, you know, quicker with the product. So you can go on to the next slide now, Pravi. And for an overview of our data, we split it up into both training as well as testing. So training images, we have 4,900 virtual world images, and these have a wide range of different weather and lighting conditions. And then we also have a small amount of real world images as well. And then testing images, we have both virtual world images again and real world images, but these ones are more, I'd say, difficult in that they have very large amounts of glare and heavy rain and things like that. And you can see what these images actually look like over on the right hand here. So here we have the RGB image on top, and then the lower image is the classification of the of each and every pixel on the image. So we classify it as road or light or lane line, all these things. Okay, and then for ways to potentially tackle the problem, you could do data augmentation. So this would be transforming the images through cropping them or randomly flipping them, rotating them, things like that. Or you can do more, complex data augmentation as well, but you can't try to augment the data by just grabbing other online images. So only permitted to use the images that we provide, but you can augment them however you want. And then you can also look at different types of model architecture or methodologies for training. So these could be unique losses or constraints or regularization, things like that. And yeah, that's about it. So good luck, everybody. Thank you.
Right. Also, thank you, Jordan. And also just Maxim posted an archive paper about the different domain adaptation techniques, an overview paper. So if anyone interested in solving this challenge, just check that out as well. And thank you, Maxim.
Actually, I wonder if we are allowed to ask very quick questions.
Yes, please.
Yeah, I'm just, this is a very interesting challenge, and I'm not sure what the rules are. I'm actually interested in, but sort of tackling it. But I'm just curious that we're talking about domain adaptation, and you have training set, and then you have test set, and then I assume you have some. So what is even if it works? It looks like there is a third domain, which is the sort of real world. Where data can come from a different distribution than in the test set. So does this challenge account for this, or should they, people tackling it account for that somehow?
I'm not sure if I.
Right. Yeah. So you train it, you test it on something, and then you have an actual autonomous vehicle that drives on a road, and it might see some objects that were not a part of the test set because it's impossible to account for everything in your test set. So how is it going to adapt to that situation?
Okay, I see. So you're asking about like new objects.
Yeah, and I guess so. Does uncertainty quantification a part of this challenge, or not really? Like basically, saying how confident it is in the predictions.
Oh, no. So we'll only be looking at how accurate the classification is. So like what you see on the lower right, these classifications, how accurate those are to ground truth.
Okay.
So we're not looking at different, confidences or anything outside of these classes that we have here. There's like 10 classes, I think.
Okay, so
like
okay, so I guess my question was, what if in in the real life you will see class number 11 or class number 12?
So so let me just pause you there because we are running on a tight timeline.
Oh, I'm sorry. Yeah. I'll message you in a private chat. Yeah, sorry about that.
Awesome. Thank you.
Sure. Yeah, that'd be easier. Right. Okay. Thank you.
Okay. Thank you, Jordan. And then we'll move on to the next one. It's about utilizing Titan Computer. So Sajal, off to you.
Thanks, Praveen. So good afternoon, everyone. I'm Sajal. I'm a postdoctoral research associate in AIMS group. So in this challenge, we are trying to analyze resource utilization and user behavior on Titan supercomputer. So Titan was one of the first supercomputers, and I think it's got decommissioned a year ago. So, but the thing is that we have plenty of operational data from its lifetime, so that we are planning to, through this problem, try to understand how people actually use resources from a supercomputer. So that with that understanding, we can design better job scheduler, and whenever a system fails, how we can deal with this. Can you move the slide, please? So yeah, I already talked a little bit about myself. And so my collaborators on this problem are Dr. ORNL, Dr. Fei Wang, and Dr. Sarporal. So their research interest lies in parallel IO, parallel file systems, and also in fault tolerance. So this problem is kind of like incorporating all of these things. We are trying to understand how people use IO and file systems when trying to solve scientific problems, and what happens when some system fails, how to kind of like deal with this, or what modifies the user behavior after in such fault. Move the slide, please. Well, so you know where to find our problems. So just go there and look at the challenge for. So yeah, so kind of like try to give you some motivation why it's important to solve this problem. So resource utilization data, sorry, it kind of like captures, so you know, when you have a supercomputer, people submit jobs to solve their particular computational problem. So each job has, the initial have some estimation about how much CPU time they will be using, how much memory they will be using, what amount of GPU and what amount of IO they will be using. And we also have some measurement of the actual amount these jobs actually ended up using. So once we kind of like go through these resources, that can help us how users from various scientific domains use HPC platforms. And once we have an understanding of domain-specific user behavior, then we can design a better job scheduler so that everyone can go through this thing. And the idea is that if we can generate insight regarding workload distribution and usage patterns from domains, so we can also kind of like be better prepared if any of our resources actually fails, what to expect, how we can actually be prepared with backup systems. And the thing is that, another thing is that with time, the scheduler performance might vary because people from domains or in general scientific community can go through different job submission behavior. And it also kind of like ties to the system failure. So that can affect multiple disciplines in multiple ways. So we want to understand that behavior. And once we kind of like develop and apply novel machine learning algorithms in understanding system behavior, and that could be actually useful for designing better HPC systems. Move the slide, please. So coming to the challenge questions. So just to give you some idea, we have actually two different data sets. One is on the resource utilization. So that would actually give us per job, how much CPU usage, how much GPU usage, and IO and other things. So the problem one is stating is kind of like try to understand the user behavior in a very high level. So perform an exploratory data analysis on this rare data set so that you can see how this, it's a high level idea about resource usage. And a supplementary question could be, is there a relationship between client CPU memory usage, GPU memory usage, and other job size? So if your job size is large, the resource utilization might be larger. Second one would be extract the project information from the command feature given in the rare data set. So when you kind of like look in the job submission script or the command, can you kind of like identify which discipline it actually, or what is this project is about? And then you can do an unsupervised machine learning on clustering different apply the clustering so that you kind of like, by looking into the resource utilization, you can say this belongs to this domain or the other. And then the next one would be more like asking about prediction tool. So if you look into 7 days usage pattern for a particular user, can you actually predict that, let's say next 7 days, what would be the requirement for this one? And also you can look into if there is any seasonal impact on such predictions, because depending on, I guess, month of the year, the different user can actually work in a different productive level or something like that. So you can use some regression model for that. So next slide, please.
Right. Oh, we have more questions.
Yeah. Sorry. So the fourth question is more involved. We are kind of like trying to link the two data sets. So we cited 2 publications, which is kind of like coming from our from our data sponsors. So you can look into those papers for better understanding of these 2 data sets. But the idea is that we observed at some point, some of the GPUs are malfunctioning. So that means that in the Titan's cabinets, we kind of like had to switch to the GPUs periodically, sometimes for maintenance, sometimes following some failure. But within some period, those failures and swapping and replacement of the GPUs kind of like increased. And that also impacted how people are actually submitting the jobs. So they wanted to, let's say, get rid of these failures or avoid the failures as much as possible. So they probably would be requesting more GPUs. So the idea is that, can you link these 2 data sets? When the GPU failure happens, how does it actually changes the resource utilization? So that would be kind of like the predictive analysis in the change of GPU data set and the change in the RAR data set. And you can actually look into these 2 data sets based on different timeframes and see how they are correlated. Next slide, please.
And can you wrap this up in like 30 seconds, please? Here.
Yeah, there's the final slide. So yeah, I mean, for potential approaches, these 2 accompanying publications that's cited in the problem description is actually really helpful. So I took one of these figures. So you can see this is the GPU failure occurrence over the years. So you can see there is a hike between 2015 to 2018. So you can plot the similar plots for the RUR and then find some sorts of correlation, and is there any time gap between these 2? So yeah, that's that's problem about. Thank you.
All right, thank you. And we could take a question, but also trying to run on time. So we'll move on to the next challenge. But thank you very much, Sajal. And Melissa, this is one of our, one of the most participated challenges in the last year, the data set from Melissa and Anne. So.
Well, thank you very much, Pravi. So my name is Melissa Allen Dumas. Can everybody hear me? Can you hear me, Pravi? Okay, good. And so I am a research scientist in the Computational Urban Sciences group at ORNL. And you can see here that I'm part of a very large team. And the reason this team is so large is that we are all looking at how can we make cities sustainable from different perspectives. And you'll see that in our data sets as we go along here. And next slide, please. So the data sets that we have for you are all about the city of Las Vegas. And that is because we just happen to be looking at this city for one of our projects. But what we are interested in learning about this city is how its buildings interact with its natural environment, and then how the occupants of those buildings influence what those buildings are. And then knowing all of that, how do we expect this city to grow based on some of the information that we have about the buildings right now? So we can go to the next slide. So this is the data that's included in the challenge. And the first data set that we have for you here is a shapefile. Oh, am I? Okay.
Yeah.
I thought
No, you don't have to print out something. I'm just trying to remember the website. Yeah, I was looking at Blue and Canva. No problem.
Okay. So the first data set we have for you is a building shapefile data set. And this is something that gives the building footprints, building heights, the distance that the buildings are from each other, a little bit about what the space is like in between the buildings. And so this is what we would call the morphology of the city. And this is, to some extent, what the rest of the data that we have for you is based on. So that's kind of a good way to get started, to kind of look at what the layout of Las Vegas is, and then start thinking about what the relationships between these buildings and the rest of the data that we have might be. So the second data set here is building archetypes for the city. And we do have the creator of this data set online with us now. So if you have questions about this, he would Joshua New is the person that created this data set, would probably be able to give you some answers about that if you have those questions later. But these are basically the types of buildings that are in the city. So for instance, there might be a certain number of supermarkets in the city. There might be a certain number of, commercial buildings. There might be government buildings. What is the building type and what is it used for? And what's sort of the distribution of that type across the city? And then the number of stories, the building height, total floor area, various different aspects of the building, and how those aspects of the building will contribute to its energy use. And next slide, please. This next one is census block group summaries of building characteristics pertaining to construction type, quality, parcel layout. This also is the data set that deals with the demographics of the people that are either residents in a residential area or the types of companies that are housed in the commercial buildings. And based on this information, you can get a little bit of an insight on how the people in the area are influencing the building types. And then finally, we have census tract level files containing 100-meter resolution urban parameters. And also the creator for this data set is on the line with us as well. This is Levi Sweet that created this one. And basically what this is looking at is the parameters of each building. So for instance, frontal area density and plan area density refers to the footprint of the building, and then the area that is around that footprint. It will, in several different vertical levels, give you sort of a vertical slice of what that building and the parcel that it is on looks like at several different vertical layers. And you can see where that you can locate that data set as well. So let's go to the next slide. And this is our challenge questions. And one of the things that we want to invite people to do here is certainly use the data that we've provided, but if you feel like you've got a great idea for a paper or a great idea for a study that would involve bringing in additional data that would help you, absolutely feel free to bring in any additional data that you would like. What we're trying to find are the patterns and the relationships among these data sets that we have. And so even though these questions are here, we invite you to even come up with some of your own questions as well, because we just want to see what you think are the interesting patterns and relationships here. So question number one, how does the number and arrangement of buildings along with the building surface to plan area ratio in a given block group relate to building construction quality and value? What is the distribution of commercial, industrial, and residential buildings within each block group? And then do these distributions correlate with building age or building value or building size? And then using temperature data from some source that you might find. NOAA is a good place to look at different weather data, but using temperature data. Are there locations within the city that tend to be warmer than others? So can you take a look at the urban heat island effect with this data? And then how does this relate to the building density and the building type? Also, how does the built environment and the local scale experience of heat co-vary with socioeconomic and demographic characteristics of residents? There's been quite a bit of study on this that's been brought out recently. And so maybe you can find some of that within our data here too. And then finally, if you are interested in looking at how landscaping within the urban area can affect area's heating and cooling, and then the actual building energy use based on that heating and cooling. You can bring in your landscaping data and take a look at that in addition to what you're finding in our data. So those are our challenge questions, and we invite you to be creative with the way that you approach our data. And that's all.
Thank you, Melissa. So I have one question. So the goal of answering all of these questions is to identify or develop a better infrastructure. So what is the overall overarching goal of, like, combining all of these data sets, answering all of these questions?
Yes, so our overarching goal is basically sustainability. How do we design sustainable cities? And so based on the previous research that we've done, we had seen that sort of the arrangements of buildings in the city affected the local meteorology. And so based on that idea, we want to know what else can affect the efficiency of building energy use in an area. And so we've got some socio-demographic data here, and certainly, as I said, people are welcome to bring in other data that, that would have to do with the environment.
Awesome. Thank you. Does anyone else have any questions? All right, let's move on to the challenge 6. We have 15 more minutes, but we also need to rush, I think. So anyway, Maxim, off to you.
Hi, thank you. Sorry for taking too much time with my question earlier. So I'll be very quick on this challenge. So, okay, basically, the challenge is about finding optimal scanning paths for microscopic measurements on the atomic scale. So if you could just go to the next slide, please. Thank you. So basically our data set that we provide here is a movie, which is, sequential measurement of the same area of a particular sample with a scanning transmission electron microscope. And so this sample is a 2D material called graphene. So ideal graphene is composed of, it represents ideal honeycomb lattice, so a bunch of hexagons. But real materials, they have these very interesting defects called topological defects, such as 5-7 reconstruction, 5-8 reconstruction, and so on. And so these are usually the points of interest. So we are not really interested in like this very large, bright area on the right side, which is just amorphous part of a material, but we're really interested in visiting those defects and perhaps zooming in, doing some other types of measurements on them. Because this type of defects, they actually can be used to control materials' electronic, magnetic, and optical properties. But in any case, so a standard scan is done, it's called raster scan. So you actually go through every pixel on your grid. And so while the information of interest is concentrated in just very, very small regions, so less maybe than 10% of this entire grid. And so the question is how we can visit the maximum number of points of interest within the shortest amount of time. And the reason it's important, then one thing I didn't mention, that when we scan, we also affect our sample. We actually kind of destroy it, so it starts to fall apart. So we want to visit maximum number of points of interest before our material gets destroyed. So if you could just go to the next slide. Thank you. Yeah, and so here, if you look at the challenge, there are much more details in there, but basically there is a need for efficient exploration of the sample, looking for the elements of interest. And so here in A, this is a standard raster scan, which is not very efficient, but then maybe you can just go to the specific location and do certain type of different scan forms in there, or you can just move from one point to another, do this sparse scan, and then do some reconstruction with something like Gaussian processes. So anyways, there are many ways that this can be done. And so there is a lot of room for experimentation. And you have a data set that can be used to create this virtual microscope. Just imagine that you actually are scanning. The techniques that can be used are Gaussian processes, Bayesian optimization, perhaps reinforcement learning. So take a look at the challenge. There are much more details there. And if you have any questions, email me. If you have a need for more data, also email me. We actually have more data. Okay, thank you.
Thank you. Does anyone have any questions? So I have a question. What is the dimensionality of the data set? Because one of the things I work with, some of the microscopy data sets are very high dimensional. So,
it's okay. So there will be challenge number 8, where we will be talking about high dimensional. So this is just 2D. So these are just it's just like a movie. It's actually like movie is just a sequence of frame, right? So this is also a movie. So a sequence of 2D images obtained over the same sample area throughout the time. So.
All right, thank you. I probably not that one. Okay, thank you, Maxim, and we'll see you back in challenge 8. So again, we'll move on to challenge 7. Yeah, and then John, you can go ahead.
Okay, if you can see me and hear me.
I also want to just add here. So until challenge 6, they're all data analytics challenges where you can use straight up machine learning. And this is challenge 7 and 8 are edge computing challenges. So one of the things about edge computing is you want to predict things more in a real-time basis, and you also do not want to go move all of your data into a central server, but instead you want to use these, you want to compute your results much closer to the instrument or the machine instead of doing them in a batch processing kind of way. So edge computing challenges are challenges 7 and 8. All right, sorry, John.
Thank you for the introduction. So my name is Jean Billeux. I'm the computer instrument scientist for neutron imaging at the SNS. Quick 101 of neutron imaging. We are taking pictures like we do, like you do with any cameras, but we don't use photons, we use neutrons. So we take picture of neutrons. And the main challenge of those detectors that have been used for many years is we use roughly the same chips as the one you have in your camera. And you notice when you take very fast picture, a lot of them, it takes some time for the camera to load and save them. The problem is for our case, we want to take thousands of pictures per microseconds. The reason is we want to take roughly a picture for each neutron energy. So we came up, not me, but some guys came up with a new technology of detectors. And we were lucky enough to be the first one to, yeah, you can go straight to the third slide. So we ran an experiment a few weeks ago using that Timepeaks-3 detector. And we were the first one in the world to take those kind of data. And that will be the one you're gonna work on. The challenge of those guys is for every neutrons hitting the camera, the MCP detector, that's the name, it creates a cluster of counts in the back, and that's the one recorded by the detector. So that means it's kind of blur the image. The challenge will be to remove that blur, and all those events, they form clusters like a potato you throw on the wall. And you need to isolate those clusters, and you need to find where is the initial event. Is it in the center? Is it just roughly on the side of the center? We don't know. And that will be one of the first questions of this challenge. And if you can do that, we can increase the resolution from roughly 50 microns right now with the detectors. We think we can go to a few microns of resolution. And why is this important? We have ESS. I don't know if you heard about this. This is the European Spatial Neutron Source. They are building the same kind of facility as SNS, so billion-dollar investments. And they are looking at using the same detector as the one we are developing right now. So if you can come up with a code that can isolate those clusters, find the center, and improve the resolution, those guys will jump on your code and use them and use the code over there. Same thing for JPark and the Chinese Spatial Neutron Source, same thing. All those guys are just staring at us right now to see if we can come up with a solution. Thank you.
And then, does anyone have any questions? And then we'll move on to the last challenge, pretty much exactly on time. So we have 5 more minutes. Thank you, Maxim.
Right. Hi, everyone again. So this challenge is about using active learning for efficient sampling in multidimensional spectroscopic measurements of nanoscale materials. So let's go to the first slide, please. Oh, I didn't realize they actually have animation. Could you just show all of them, please? Thank you. So basically, the general idea is that we have a technique that measures surface properties. And so for each XY point on the surface grid, which is up to you how dense this grid is, but let's say you have 1024 by 1024 grid. And in each pixel on that grid, for each pixel, you can measure you can perform some spectroscopic measurements. So it could be something like measuring differential conductance as a function of applied bias voltage, but you can, and other type of spectroscopic measurements could be performed. And so basically, in the end, you have a multidimensional data set where for each XY point on your surface, you have multiple spectroscopic measurements. The problem is that acquiring those measurements is very time consuming, and especially when you apply high voltage to your probe, then what happens is that you are not even able to complete the entire experiment because your probe will get destroyed, right? So, but at the same time, similarly to what I mentioned in the challenge number 6, the behavior of interest is usually localized in some relatively small regions of this configuration space. And so the question is, instead of measuring every single point on the surface grid, as well as in your spectroscopic dimensions, can we actually come up with some more efficient sampling technique? And if you could go to the next slide, and probably makes sense also to show. Yes. So basically, do we even need to perform measurement in each pixel to learn about the information of interest? And we already had some preliminary results that shows that no, that in some cases we can just measure 10% of all the pixel and then use techniques such as Gaussian processes to reconstruct the entire high multidimensional data set. But the challenge, so this has been mostly done offline, but the challenge here is how we can do it online. So how we can perform efficient sampling for our multidimensional spectroscopic measurements in real time. And this is the major challenge because it's one thing to do sparse measurement and then reconstruct it afterwards. And it's completely different thing to be able to sample this next most promising point in a fast manner, so that we're talking about seconds, and maybe even, well, yeah, seconds. And so there is a connection to a DGX2 box. So if you can come up with an algorithm that is parallelizable on up to 16 GPUs, that can perform this that can predict the next measurement point based on the point that we already measured in a very quick fashion. So talking about seconds here, then it will be very nice. It will be a real breakthrough. So that's the idea.
Fantastic. Thank you very much. So does anyone have any questions? So I do. One of the things is all of this particular identifying the next best scan point, that kind of, it needs to be done in a real time, especially when the scanning is already happening, right?
Mm-hmm. Yeah. So it's basically in the end of the day, it should be fast enough. I mean, we want to do more efficient sampling. So I mean, the selection of the next point should be fast enough so we actually have some advantage over just measuring this HI grid as we used to do. So yeah, I mean, it should save time. If it takes so long that it's actually easy just to do it in the old way, then what's the point of using this approach?
So what would be a good point right now? Bayesian inference, is that a good?
So yeah, so this can be, yeah, I mean, this kind of things can probably be done either with Bayesian optimization or reinforcement learning. We actually are exploring the Bayesian optimization approaches. And what we found so far that off-the-shelf methods, off-the-shelf acquisition functions, off-the-shelf kernels do not really work very well for our type of problems. So some customization is necessary, perhaps. So I would recommend looking into something like deep kernel learning, defining your custom acquisition functions instead of just using the off-the-shelf ones. Could be helpful. Now, one other thing I would recommend is that don't reinvent things from scratch. If you're using Bayesian optimization, there is this very nice toolbox from Facebook called BotOrg. So it needs to be customized and adapted to this type of measurements, but it already it already runs on GPUs. It can be easily parallelized because it's based on PyTorch library, but it needs some adaptation and customization for this type of data.
Awesome. Thank you, Maxim. And that concludes the end of all the explanation of all the different challenges. So, so if you're a sponsor, and I see a lot of sponsors here, please advertise this data challenge, because one of the things is we want people to explore. And one of the big reasons I came to a national lab is because of the amount of data sets that there are. And that's my favorite part about working at a national lab, the amount of science I learned. So we want people also to know the coolness of working at a national lab. So please advertise this data challenge. And also, if you have any questions, please contact me at my email or the data challenge email. And please check out the website for any updates. Also, thank you very much. Appreciate it. Thank you very much for being here.